Hey there, I'm Neil Knobloch, a faculty member here at Purdue University, and I'm excited to share with you this module on how to apply scientific reasoning in your classrooms. So we will go through this module here in the next few minutes, and we'll show you that we're on this pathway of the roadmap for doing the scientific reasoning process, starting with data and evidence. In Module 1, you went through scientific investigations with Module 2, and then you focused on reasoning in Module 3. And now we are completing this roadmap with the fourth module focused on scientific reasoning in your classroom. How do you apply this as we go in and work with students? And so you'll see that this module lays out kind of a summary of the process that ties it all together. There are 8 steps, and we're going to just walk through these 8 steps. You'll see it's very similar to problem solving. It starts with recognizing what the problem is, and then trying to answer a question using inquiry, predicting the outcome using a hypothesis, or thinking like a hypothesis about a hypothesis, then identifying what data, information, evidence you'll need to answer the question. Also gathering data, then assessing the phenomena, making inferences with new or existing information, and then last, you'll make a scientifically sound decision. So let's go through the first step here, and that is recognizing a problem, and that is using the food system STEM project that you have been working on with your students or will be working on with your students. Think about a problem, a specific problem that you want to know more about. Some ways to identify a problem is to think about what previous knowledge and or experience do you have that helps you think about what this phenomena is that you're working on. We're going to use hydroponics as an example. So you'll be thinking about, have you ever tried to raise plants before? If so, have you tried to do it hydroponically? And so what did you learn from that experience? What problems might you know could occur? And that could help you frame it. Also, you can think about, did something happen as you were raising plants or growing your plants hydroponically, and you want to know more about what might have caused that. So you'll see the example that we use, the plants were elongating, and we're going to think about what might have caused that. Some additional things to think about is, does an input or the way in which you raise the plants, in this particular example, provide better results? Or maybe provide a more efficient way to get similar results. Maybe a more energy efficient way, for example. A more cost-effective product or outcome. So is there some way you can maybe reduce your inputs and still be able to get similar results? So it's more economical. It's also thinking about, how is this more environmentally sustainable product and outcome? And so are there some things you could try there? And then lastly, is there a more socially responsible product or outcome that the consumers might find even more beneficial in alignment with the values that they have? So as we think about the problem, we are revisiting a model that we shared in some previous modules when we talked about integrated STEM. And you'll see that that is pulling together the multiple disciplines of science, technology, engineering, agriculture, and mathematics into a more integrated approach to learning. We then are going to talk about the design challenges and constraints here after we talk about the top triangle piece, and that is this module, series of modules, has been focusing on thinking about design solutions. How do you apply scientific thinking and evidence-based reasoning using this food system design challenge and help students make more informed decisions? So now as we think about that decision that you're wanting to make, how do you frame the problem? How do you problematize what you want the students to investigate? And so do that by thinking about maybe some different challenges and constraints regarding the design of that. And that could be, as we just showed in a previous slide, based upon social responsibility. This is, how do consumers perceive that this product or this product was raised in a socially responsible manner, that in which aligns with their values as a consumer? How is it economically viable? How is it done in a cost-effective way? Think about the third factor here, and that is how can it be more productively efficient? So how do you grow plants in the most efficient manner, for example, in our hydroponics example? And then you have environmental sustainability, and we think about energy. How might we do this in a way that uses less energy? And so we could frame our question around any of these factors and try to get the problem narrowed down so that we can then test it and see what we can do to make a better decision regarding our hydroponics, for example. So let's go through these steps. Now that we've identified a problem, there are some additional steps we want to go through in thinking of, in doing scientific thinking. And so this first step is to identify a question. So now that you're thinking about a problem that you want to use with your food, or at least frame using the Food System STEM project, identify a specific question or questions that would help you improve your project or make a decision based upon evidence. A couple examples we have here related to the Food System STEM project would be hydroponics. How do plants respond to light? Light source that is 12 inches versus 24 inches above the plants. And another example, if you're working on food safety, is which hand soap had less bacteria growth if you're going to try to have handle a food product in a way that would be safer. We're going to work through the hydroponics example in particular, but we did want to share with you a couple ways of getting to identifying a question with two different projects in mind. So the second step is to predict an outcome. So based upon your Food System STEM project, predict the outcome to the question. Basically, attempt to answer this question. And so the hydroponics project, plants will grow longer or be more extended if the light source is higher above the plant. Why do you think that? We'll go through that later, but basically, if plants are further away from a light source, based upon some of our own experiences, even in our houses, you'll see plants trying to stretch and bend towards the light. So that's why we came up with that prediction. Then for food safety, we're just going to say that maybe you get what you pay for. So more expensive hand soap is going to have less bacteria growth than less expensive hand soap. And so that's just a prediction that we're going to throw out for the food safety project. So next, we're going to go to this third step, and we're going to identify what data, information, and evidence you need to now answer the question. So based upon the food system project that you have been working on or will be working on, identify what data, information, and evidence you'll need to answer the questions that you have. So using the hydroponics project as an example, you're going to set up two light bulbs located at 12 inches and 24 inches above the plants. Then we're going to take pictures of the plants, and it's set up a camera so that it's always in the exact same spot. That's what we mean by standardized process. And we're going to take pictures every 3 days. And we're going to print those pictures out. And we're going to then be able to measure the plants off of the pictures as well, physically measure the plants, but we're also going to be able to use the pictures to do the comparison and confirm our measurements as well. For food safety, we're going to have students wash hands with two different soaps using the same procedure. So make sure that they do exactly the same steps, same amount of soap pumps, or the same amount of soap with each pump, the same number of seconds washing their hands, etc. And so a standardized process is very important there. And then they're going to touch an agar plate after each hand washing. And then we're going to take pictures of the agar plate every day for up to 1 week to be able to measure the amount of bacteria growth. So as I mentioned, we're going to focus a little bit more on the lighting or the hydroponics example. And so this is a picture of one of the projects at a school, a high school. And you'll see that it has 3 different levels, and they have lights on the third. So if we look at this, the top level, the lights are about 24 inches above where the plants medium are growing. And then if you look at the middle level, that's about 12 inches above the plants. And so you can see we're just simply pointing out that this design that they made, they had two different levels of lighting above the plants. And so now we're going to see, okay, what might have been the results of the distance of lighting from the plants on the plants. So step number 5, we're going to gather the data. So again, based upon your project, we want you to gather data to answer your questions. And so what observations or measurements can be made is something you'll want to think about. And we shared with you in a previous slide what we were thinking about in our examples. You also want to think about who could you talk to, some experts that could provide you information and help you gather additional information that may not just be from the experiment you might be doing. And so it's always good to reach out to experts or people that have had previous experiences and knowledge in the area that you're working in, and they can give you some insights as well. You also might think about what sensor could be used to help you gather the data to answer the questions. And so there are a number of sensors out there. We've talked about these sensors in some of our workshops with teachers. And so if you go on our website, you'll see there are some presentations that break that down. And so I'm not going to spend time on that, but I'm just giving you the heads up that yes, sensors are a really useful tool to help gather data. And then the last question is, how will the data be collected and organized? And so you can gather the data in a sensor, or you can manually input it into a Google Sheet so that you can then start to do comparisons, make graphs, and start to look at, do you see any patterns here or any differences between your control and your treatment? So back to the lighting example with the hydroponics project, you're going to make an observation and you're going to do a measurement. So the observation, what do you see? And if you study these two levels, the top level, the plants appear to be taller, right? And if you look down in the middle level, the plants are not as tall. And so now you're going to start asking the question, well, what's going on here? Why would the plants be taller if the light is further away from the plant versus if it's closer? And so we actually take a measurement, and yes, we found that the top level, those plants were 20 inches tall, and the middle level, they were 10 inches tall. So you can see the plants on the top level were taller. Let's go to step number 6. And you'll see that this is assessing the phenomena, which means think about what's going on. So using your project, your STEM project, think about the phenomena both rationally as well as logically. So analyze the data from multiple data sources. So in the previous slide, we had observation and we had measurement, right? We could also then consult with experts and other sources of information. For example, extension websites have information about hydroponics that could be very useful. There's webinars and there's podcasts and other sources of information that could be very, very useful for you to think about what's going on here and just become more familiar with, okay, what's going on when we have the plants underneath a light that's at 12 inches versus 24 inches. And then also think about other alternative explanations of the data. Sometimes students just want to think about one explanation and they stop because that's makes sense. They got one answer or one prediction or explanation, and so we'll just stop there. But it's always good to think about what other explanations might be going on here that you could use just to try to stretch your brain and think about something that also could be considered, and make sure that you do research or ask consultants, are there other reasons why these plants might be getting taller and not just because of the light? So that's just a good reminder to be thorough. So back to our hydroponics example, you're going to consider at least two sources of data, right? And we also have, we've showed you those in the previous slide. So are they consistent? When we look at the plants and we measured the plants, yes, they were consistent. The top level is taller visually, and they were also taller using our ruler. So then you think about, okay, what's going on here? So why do you think the plants are on the top level that are on the top level are taller? And so your prediction was that they would stretch towards the light because plants need so much energy, light energy, so they want to get closer to the light. This light is artificial, and so they're not getting maybe the same amount of energy like they would if they were outside in the sun. And so it's like they're being starved, if you will, from light. So therefore, they're trying to get closer so they can get more of that light energy by just being closer to the light. Plants that are 12 inches away on the middle level, they didn't have to stretch as far, so now they're comfortable because they're within just maybe a couple inches of the light. And so they're getting the light, as much light as they could get because they're just closer to the light. So we just kind of thought about what's going on here with the phenomena. And now we're going to take step number 7 and we're going to make inferences. So we're going to think about, what does this mean? And we're going to use our current information, the new information we have, as well as any other existing information from other sources. And we're going to try to essentially make informed educational guesses, or what we're going to say inferences. So what do we think this means? So using the data that we gathered and the expert informed sources, we're going to write out some logical reasons of what we think the data means. And you just heard me say in the previous slide, my own thoughts. Now I would write them out, right? And so I would take time and meaningfully think about, okay, this is how I would communicate this. Because as scientists, engineers, agriculturalists, we think about how do we communicate, and that is not only just orally, we want to document by putting it in writing. So we'll also write out an argument of why we think that is what's going on. So that's an explanation argument. It's like an explanation. We use the data. And so this would be the argument that plants closer to the light they won't get as tall because they won't have to stretch toward the light. And we just talked about that with light energy and how plants gather light energy by being close to the light if it's a lower level light, an artificial light, for example, in this case. And then consider the strength of your argument. Think about, well, what limitations are there? Are there other things that could explain what's going on here? One thing we don't know is, were they getting the same amount of fertilizer? So the top row, maybe they were getting more those plants were getting more fertilizer than the middle row. Or maybe the top row was getting a different type of water. We probably assume that they probably weren't, but I'm just giving you examples of, think about other variables and how they might be contributing to the results, because you didn't test for those, right? So it's just showing you're just being you're being thorough in your thinking and your argumentation. And so the example here is plants elongate or stretch and get closer to the light when they are not getting enough light in an indoor setting. So here is our inference, and then we would go ahead and work through that argument, explaining why we think that's the case. And we would also think about other tests we would do to just confirm that it's not something else that would be causing them to stretch or get taller. So we get to the 8th step. This happens to be the last step of the scientific thinking process that we're sharing with you today. And you want to make a scientifically sound decision. So again, using the project and the problem that you've been working on, use logical reasoning to make a scientifically sound argument to improve the project. So what conclusion can you make based upon the evidence? Well, we're going to conclude that the light that is higher above the plants is going to make the plants stretch. How would this conclusion help improve your project? Well, we don't want those plants to just get leggy and stretch. They actually get weaker and they don't stand up as well. So we're going to move the top row of lights down so that it's closer to about maybe 12 to 16 inches away from the plants, okay? And then what else might you want to know? One thing you might want to know in this hydroponic example is that enough light. So should we add more lights? As you saw there, I think there were just 2 lights on each of the levels. The other question is, are they giving enough light? So we know how bright the sunshine is, and it's natural, and plants around the world grow really well when they get the natural sunshine. But when we use artificial light, it may not be as high of lumens, is what they call it, or intensity of light. So we're going to want to find out, are those lights, they were LED lights, were they giving enough energy for the plants to truly get the full benefit of what they need to grow indoors in a hydroponic setting? So what would your next inquiry be? Well, if that's the case, maybe we could order some new light, after we could lower the top level and try to see if growing some new plants, if they don't grow as tall. Or wouldn't it be cool to get some new lights that are have higher lumens? Or we could do, sometimes you can study cool versus warm lights, because you can buy these LED lights and you can see that there's also the different type of spectrum of light that's there. So we could do a test on that. You can just see that just because we picked lighting doesn't mean we've answered all the questions about lighting in the way that we looked at it. We just looked at height today, but you could look at the amount of lumens. You could look at the also then the color, the amount, what color, type of color is in those LED lights that we're talking about. So did we make a scientifically sound decision? We worked through the process. Hopefully we did, because we used evidence and did it in a way that also was informed with the experts and other strong sources of information out there that led us to improving our project. So in this example, it just says, moving the lights closer to the plants, and for the next inquiry, we can see how much light plants need in an indoor setting, as we mentioned, with the different types of bulbs, maybe a higher lumens or a different color spectrum. So you've just walked through the 8-step process of applying scientific reasoning using a couple real-world examples in your classroom with your students. And so congratulations. Feel free to walk them through these steps. It's pretty logical, right? And systematic. So it's just important that they do break it down, and they're working through the process in a way that they can make strong evidence-based and scientific decisions. So an opportunity for you to continue your professional development and growth is to think about some reflection questions. So you can see there's a model on the right-hand side, and we're going to ask a few questions here. How does scientific thinking help you think more deeply about the problem? It's a great question for your students as well. How did the framework on the right-hand side help guide you through the scientific thinking process? And you can see we pointed to some of the 4 different factors that you might think about framing your problem. And then what types of reasoning did you use in this application exercise? And so was it deductive, inductive, or abductive? And so you can revisit the previous module if you need to brush up on what those are. But you can use any of the 3 types of reasoning, and you may use maybe a couple sometimes when you do your experiment. So just be mindful, there are different types of reasoning as you work through solving problems within a scientific thinking method. Just want to acknowledge that this is part of a series of modules for online professional development. So feel free to check out the website where this module will be stored, as well as the other modules. Feel free to reach out to me here at Purdue if you have any questions. And you'll see that this grant was funded with a USDA NEFA grant, and we're very grateful for the support we've received to be able to do this project. Also want to recognize my colleagues, Dr. Weiwei Wong and Ms. Brianna Nelson, for their leadership on this project and everything they do to make things happen, as well as Dr. Crystal Hands, who was a content consultant for this module. Thank you for your attention, and we wish you well in applying scientific thinking in your classrooms.